It is recursive. It is fun, recursive weirdness. So today we're going to take a little bit of an aside and talk about an application of matrix multiplication. Again, this should be under the handouts, the content handouts, linear algebra, maybe, I don't know, one of the handout sections in D2L. Should be in 11.1 Markov chains, 11.1 through 11.4 Markov chains labeled file. So again, this is chapter 11 in the Intro to Probability book. But suppose after all of the, basically after Julius Caesar, there are a lot of dead bodies lying around. And then the zombie apocalypse happens. That's how we're going to tie it in to that. So the zombie apocalypse has happened. And you've managed to survive, at least for a few weeks. Eventually you're going to die because that's how all the zombie movies end. You've got the group of survivors at the end that you think are going to make it, and then, you know, something happens. Yeah, they're not going to make it. So they think they're safe on the island or whatever, and then something happens. But you've survived for a little bit, and as time passes, you make some observations that there are 4 classes of people, roughly. Those who are normal and not infected with the zombieitis or whatever it is. You've got people who have been bitten but have not yet become zombies. You've got those who are zombies and those who are dead. And so there's all this sort of transitioning between these groups. You know, you're fighting the zombies, you're trying to sort of kill them, but being zombies, once you kill them, then some of them maybe aren't successfully killed and they come back as zombies again. We're going to introduce an element that the zombie purists among you may contest. We're not going to necessarily follow the normal zombie trend, but there is a chance of recovering. So normal people have a 20% chance of staying normal. They have, on a given day, 20% chance of staying as you are, 70% chance of being bitten by a zombie. Otherwise, the movie's not that interesting. You got to kill people off pretty quickly, or they have to be infected pretty quickly. You've got a 0% chance of becoming a zombie, because if you are normal, then you have to be bitten first before you actually become a zombie. So there's that intermediate phase there. And you've got a 10% chance of just dying because of maybe something else that happened in the zombie movie. Yes?
I'm not able to open the file for some reason.
What?
I also don't have the file.
Okay.
It tries to open the normal window and then it just...
We're going to pause. Can I pause the recording? Resume that. Unmute that. All right. So we've got normal people, 20% chance of staying normal, 7% chance of being bitten, 0% chance of becoming a zombie, and 10% chance of dying of something. Those who have been bitten have a 5% chance of recovering and going back to being normal because for whatever reason it didn't take. They have a 5% chance of being bitten again because the zombies aren't as interested in the people who have already been bitten. They can sense that for whatever reason. And we've got an 80% chance of becoming a zombie and a 10% chance of dying because in a lot of the movies they're just like, kill me before I turn into a zombie. And so then that happens. If you're a zombie, you've got a 1% chance of becoming normal. You've got a 0% chance of being bitten by a zombie, so we're allowing for a little bit of recovery here just to keep things a little more interesting. But the zombies aren't going to bite the other zombies. Again, depending on the movie that we're in, maybe that's not what actually happens, but that's what we're going with here. We've got a 94% chance of staying a zombie and a 5% chance of dying when the surviving people come and hunt you down. And then if you're dead, then you have a 0% chance of becoming normal. You have to transition through the zombie states first, but you can eventually, I guess, get back because you could turn into a zombie, and then once you're a zombie, you've got a 1% chance of going back to normal. So there is a way to get back to normalcy there. 0% chance of being bitten by a zombie if you're dead because they're not interested in you, and you've got a 95% chance of becoming a zombie that day and a 5% chance of staying dead. So that is our, I'm about to become a zombie up here, but the transition matrix that we're going to form. So we're going to have a matrix that contains all of these probabilities, and we're going to take those percentages and put them in either as rows or columns. And the convention for this book, and I think often with Markov chains, it's not quite the order of multiplication that we've been focusing on or that we've been using, but we're going to put these in as the rows of the matrix. So we've got, for the normal people, you've got your first row, the 0.2. So basically normal to normal is going to be here. And then we've got normal to, so I'm sort of indexing these rows and columns with normal, bitten, zombie, and dead, and then normal, bitten, zombie, and dead for both the row and the column indices. And so we've got the, again, the normal to normal, normal to bitten, normal to zombie, and normal to dead probabilities in here. And then we have the zombie, or sorry, the bitten to basically normal, bitten to bitten to zombie, and bitten to dead, and then zombie to each of the states, and then dead to each of the states there. And then initially we're going to suppose that 98% of the people were normal, 1% had been bitten by zombies because we need someone bitten by zombies to kick things off. 1% of them being zombies, I guess we really need those, and then we could start with maybe no one being bitten, but get this, and no one is dead to begin with at the beginning of the movie. And so we would have this vector that the book calls U of the initial states, so the initial breakdown of the population into each of the states. And after one day, we would have the following. So I'm going to define this, what's called the transition matrix, all the probabilities of transitioning from one of the possible states to the next. And then we're going to define our vector, basically, of those values. And we're going to multiply those together. And the order that we're using here is to have the U matrix vector times the zombie one because of how we've set things up. So we could switch that around and have the zombie on matrix on the left and the vector on the right, which is typically how we've been writing down our matrix vector equations. But the setup here in the book is to order the multiplication in this way. And so if we do that, in order for the dimensions to work out, I do want this vector set up as a 1×4 matrix, basically, so I can multiply it by the 4×4 transition matrix. And when we do that, and think about the way that the multiplication is going to work out, we're going to take this and multiply it by all of the different probabilities. And so we'll have the people that end up in the normal category. When we take the 0.98, I should probably write something down on these. Well, don't know that we necessarily need to do that. But when we run this, we're going to have the 0.98, for instance, to see who's going to end up normal. We're going to have the 0.98 times the 0.2. We'll end up with the 0.01 times the 0.05, the 0.01 here times this 0.01, and then this 0 times that 0. And that will, the sum of those will give us the percentage of people that are normal after one transitioning period, which we'll just say is 1 day. And then when we continue the multiplication, we'll take that vector, basically dotted with that column. And so to figure out who is going to end up bitten after the first day, well, 98% of the population started off normal, and those have a 70% chance of being bitten. So multiplying those together, we've got the 1% that are bitten and the 5% chance of being bitten again. We've got the 1% that are zombies times the 0% there, and the 0 dead, and the 0% chance of being bitten there. And so when we multiply those percentages and add them together, we're going to get the percent of the population that has been bitten after 1 day. And then the becoming a zombie, we're going to have, again, these values times all of these column entries here. We're going to have the 0.98 times 0, plus the 0.01 times 0.8, 0.01 times 0.94, and then the 0 times the 0.95. And so when we multiply all those percentages together and add them up, we get the percentage of people that are zombies after the first day. So as we go through and do this multiplication, same kind of thing with the dead breakdown. I'm gonna have that. I already ran that. We've got this. And so after 1 day, we have this breakdown in the population. Just under 20% of the people are still normal. We've got quite a few people that have been bitten. Almost 69% of the people have been bitten. Just under 2% of the people are zombies, and just under 1% of the people are now dead. And so then when we go through one more transition period, so one more day of the zombie apocalypse, then we get this breakdown. Fewer people are now normal. We've got a much smaller bitten population because most of those have turned into zombies at this point. And then we have more people. I guess the dead is actually just under 10%, not just under 1%. But we've got the dead percentage not that much different. After 3 days, we're going to multiply this vector again by the zombie matrix in that order. So I've got the vector on the left and the matrix on the right. That's why I've got the parentheses here just to emphasize that grouping, but it's going to be this vector times the transition matrix. Here we're going to multiply by the zombie matrix basically 3 times. I could just go ahead and do this sort of thing again, but we can also use the matrix power command. That's going to make things a little bit easier to do. But I could, basically what we're asking that matrix power command to do is this multiplication, where I've got the vector and then times the matrix 3 times. The associativity means I don't have to have those parentheses on there. But again, that's how we're viewing that. So after 3 days, we've got only about 3% of the population is still normal. We've got about 6% bitten. Almost 85% of the people are now zombies, and about 6% of the population is now dead. And so after a week, well, then we'll have 7 multiplications there. We get this breakdown. And again, not very many normal people left, and so there's not very many bitten people. There's not anyone left to bite, basically. And we've got the zombies, and we've got basically most things becoming zombies. After 1 month and after 1 year, you'll notice that we end up with the powers of the matrix looking like that, where everything is basically the same. And so if we do this u times that, so I'll go ahead and put those in there, u times those, well, it's not liking it, so because I matrix formed it. Don't do that. I don't really need the matrix form for those multiplications. But when we run that, notice that it's not, I mean, it's still a little bit different from what happens after a week, but between the 1 month and the 1 year, I actually don't notice any difference out to the number of decimal places it's showing us. There's no difference in the population breakdown. And so after a period of time, we reach what's called a steady state, where we have a basically fixed percentage of normal, bitten, zombie, and dead. And so this is what the population is sort of trending to over time. We're sort of taking a limit as the exponent on that matrix goes to infinity, but in practice, with a lot of the ones that we're going to look at after a relatively small number of powers, then we're not going to notice any difference. We'll be within whatever our calculation tolerance is on those. So when we're looking at these, just the power of the matrix, and let me sort of take this one and we'll matrix form that. Just so we have one where there's maybe a little bit of a difference. That one's also not super helpful. Let me just change this one. Let's make that the day 3 one. So this is telling us that after 3 days, this is what you would end up transitioning to. These are the probabilities. So if you start off as normal, then you've got a 3% chance roughly of remaining normal after 3 days. If you start off normal, then you're going to have this percent chance of being bitten after 3 days, this percent chance of being a zombie, and this percent chance of being dead. If you start off bitten, then after 3 days, you've got a, again, just for the sake of the recording here, you've got that chance of being normal again. You've got this chance of being bitten, that percent chance of being a zombie, and this percent chance of being dead. If you started off dead, then you've got about a 1% chance of being normal and a less than 1% chance of being bitten, pretty high chance of being a zombie, and about a 5% chance of still being dead after the 3 days. So as we're looking at just the power without multiplying this in, then we can read off basically from a starting state in the row, what's the probability of ending in the state indexed by the column? So starting in either normal, bitten, zombie, or dead, what's the probability of ending up normal, bitten, zombie, or dead after this many transitions? And again, here we're thinking of 1 day as one transition period. Again, if we have a specific breakdown in the initial population, then we just multiply that vector by the power of the matrix corresponding to however many periods we've gone through in the transitioning process, and then we get our breakdown of that specific population after that many days. So that's basically what we're going to be looking at in the Markov chain section. So we're going to be setting up the transition matrices. We're going to be multiplying them by the sort of initial vector breakdowns. We're also going to be looking at the powers and seeing what that steady state is, if it's converging to something. And then we're going to be interpreting that in the context of the problem. So what we're going to do for the rest of the class period is just take some time and talk to the people around you, work on these exercises from those sections, and start trying those. Again, some of these are, or all of these maybe are the homework for this section. I don't remember if those lined up exactly still, but just practicing those, and I will maybe put these, at least some of them. I don't know how many of these are going to fit, but try to get some of these up on screen. And I'm also going to stop, let's see, 2, 4, 6, and 8. And also some of these are related either to each other or to earlier examples in the section. So also need to look back at those. But 2, 4, 6, and 8 from 11.1 are what's up on the screen here. And again, I'm going to stop this recording, but if you're watching this later, then again, go ahead and practice those. And at some point, I will, before the test next week, I'll also have an updated file on D2L with the answers, or at least partial solutions to these.